All right, the last concept in the chapter 5 in enthalpy is something called Hess's law. Hess's law pretty much states that the nice thing about enthalpy is it doesn't matter how you get from reactants to products. The path at which it takes to get there doesn't make a bit of difference. What we specifically look at is what is the reactants, what are the products, what's the starting, what's the end, and we really don't care how we get from the start to the end, but in the end, the amount of enthalpy is dictated by the reactants and products. Hess's law states that if you have multiple equations that summate to an overall equation, the enthalpy of the individual steps will summate to the overall equation. So for example, in this first one here, you can see the pathway is given right here, okay? We want to see two hydrogen gas and oxygen gas going into liquid oxygen. So here is the reaction that we're looking at. Here's one path to get there. The other path is to have the hydrogen oxygen form gaseous water and then condense that gaseous water into a liquid. So there's two steps, but in the end, we still get the same reactants and the same products. We get there just going through a different path mechanism. And because of that, the amount of enthalpy of the first step directly going there will be equal to the other two steps combined together because the reactants products end up being the same thing. As you can see over here, okay, two hydrogens plus two oxygens, plus an oxygen, produces two gaseous waters. The second step, H3, is two gaseous waters being condensed to two liquid waters. You'll notice that since, much like when we did factoring out of redox reactions, since we have two gas molecules on the right and two gas molecules on the left, and we're trying to summate the reactions, just like we're adding half reactions to create the overall equation in redox, these two will cancel out because they're on each side of the reaction. What we're left with then is the two hydrogen molecules plus an oxygen producing two liquid water molecules. Therefore, these two steps summate to the overall equation, and therefore their enthalpies, if we summate their enthalpies, that will give us the enthalpy of the overall equation, which ends up being negative 136.6 kilojoules. All right, the same thing happens down below as well. Here we see graphite carbon plus an oxygen producing carbon monoxide and a half of an oxygen molecule. Carbon monoxide and a half oxygen molecule produces carbon dioxide. So the carbon monoxide molecule will cancel because it's on the right on one side and the left on the other. One half of the oxygen molecule will cancel, and we are left with the overall equation. A graphite carbon plus an oxygen produces carbon dioxide gas. The summation of the two steps together will end up being this overall enthalpy of the third. And you could always check this by using enthalpy of formation values. If we take and summate the enthalpy of the products, which in this case is the carbon dioxide, and subtract the summation of the formations of the reactants, that too will give us the enthalpy of the reaction. So we're starting to find out different techniques that we can use to figure out the enthalpy of the reaction. In this one, we're using the summation of given reactions and not having to look up the heats of formation. But if you want to check the value of the overall equation, you could easily look up the formation values and then summate and see if you get the same answer. In both cases, you should get the same value for the enthalpy of the reaction. So that's Hess's law. Now, the thing that you have to do is just do enough practice on this stuff so that you can be able to figure out how can that equation get manipulated to become the overall desired equation. And that takes some time. The concept is pretty simple. You just got to get enough practice doing the homework problems that you can figure out how those individual reactions will become the overall desired equation. All right, this first one is a one-step mechanism problem. Okay, it's a hydrogen gas plus a half of an oxygen producing two liquid water molecule. However, the desired equation, we want to get two water molecules on the reactant side, not the product side. And you'll notice that the reactants on the top equation are becoming the products. So the first step thing we got to make sure to do is to make sure that the substances are on the proper side of the reaction for the desired equation. So right away, the first thing I know that I have to do is I have to flip this reaction. I have to get the water molecule to become a reactant. Now, what happens to the value of the enthalpy if you flip a reaction? What happens to it? It no longer is negative 285.8. What happens to that enthalpy value? You're right. When we flip a reaction, if it's exothermic in one direction, it's endothermic in the other. We flip the sign. Now, does that match the desired equation? No, you'll notice that there's a 2 coefficient in front of the water molecule. So now what we're going to have to do is multiply this reaction by 2, and that gives us 2 liquid waters, 2 hydrogen gases, and 1/2 times 2 gives me 1 oxygen molecule. All right, does that match the overall equation? Yes, it does. When we multiply a reaction by a coefficient, what happens to the enthalpy value? It too will double. So we have to multiply this by 2. And we get 571.6 kilojoules per mole of reaction. Okay? So, again, that problem is a really good one in being able to look at, again, concepts of enthalpy. What happens to the sign if we have to flip a reaction? What happens if we have to magnify it by a coefficient? All right, now this next problem, we actually have 2 individual reactions, and we want these 2 reactions to become the overall desired equation. Now, what I tell students, how do I figure out what do I got to do with these equations? The simplest thing to look at is to find a unique element or reactant or product in one equation and that matches up to the desired equation. For example, in problem 2, you'll notice that carbon solid is in the top reaction, but it's not in the bottom reaction. However, it is in the overall equation. Because it's not in the second reaction, that tells me that the top reaction, I have to leave that reaction the way that it is. Okay? Not only is it on the right side, they are on the reactant side in both cases. The coefficient out in front of it is a 1, just like it is the overall equation. So that tells me I'm going to leave this reaction alone. So it's going to stay negative 393.5 kilojoules. Okay? The second equation, is there another unique substance? And the answer is yes. You'll notice that the carbon monoxide is not in the top equation. It is in the second equation, and it is in the overall equation, but you'll notice the difference is that it's on the product side. In the second equation given, it's on the reactant side. So immediately, what does that tell me? What do I have to do to that second equation? And hopefully you said you got to flip it. Okay? And not only flip it, you'll also notice that the coefficient in the overall equation has a 1 in front of it. But there is a 2 in front of the carbon monoxide in the second equation. So not only do I have to flip it, I'm going to have to multiply that reaction by 1/2. Okay? So the first thing I'm going to do is I'm going to flip it. Okay? And when you flip a reaction, what happens to the sign of it? You're correct. It goes from a negative to a positive. Okay? And there would be a 2 here, and there's a 2 here, and there's a 1 there. Now, the second thing I've got to do is I've got to multiply this equation by 1/2 so that the coefficient in front of the carbon monoxide matches that of the overall equation. So multiplying that reaction by 1/2, 1/2 times 2, I'm going to get 1 carbon dioxide, 1 carbon monoxide, and 1/2 oxygen. What does that do to the enthalpy of that reaction? Hopefully you said that's going to multiply it by 1/2 or divide it by 2. And so now my enthalpy becomes, 2, 8, 283 kilojoules, if my mental math is right. All right, so now let's see if those now will add to the overall equation. Okay, so I have a carbon dioxide on the left. Let me change my color here, excuse me. So I have a carbon dioxide on the right and a carbon dioxide on the left. That'll cancel. I have one oxygen on the left, but I have a half of an oxygen on the right. So the 1/2 will cancel, and this will be reduced down to 1/2. And that's it. There's nothing else that's common. So I'm left with one carbon plus 1/2 oxygen produces a carbon monoxide. And you'll notice that that matches the desired equation perfectly. So, key concept here, find elements that are unique, that are in one of the given equations and is in the overall equation, but is not in any of the other ones. Once you find the unique substances and make sure they are placed on the proper side and to the proper coefficient, usually then the reactions will then summate to the overall desired equation. All right, last thing here, to get the enthalpy of now this overall reaction, we now just simply have to sum up the two values. So negative 393.5 plus a positive 283. That's going to give me a negative looks like a negative 110.5 kilojoules per mole of reaction. If you just had kilojoules, that'd be perfectly fine because that's what they gave you. But we'd have a value of negative 110.5 kilojoules for the answer. So that's Hess's law. All right, go ahead and try to do problems 3 and 4. I'm going to pause the lecture now. The next time I do start it up, I will have completed both of these. But please stop the lecture now. Try to do the problems and see if you can get the overall equation. In number 3, you're trying to get this. This is the equation that you're trying to find. And in number 4, you're trying to get this equation. So you're going to use the two equations given, get them to summate to the overall equation, and therefore find the enthalpy of that reaction by using Hess's law.